In the last lecture, we talked about plane mirrors, and now we get on to spherical mirrors, and there are two types, concave and convex. In this lecture, we will talk about concave mirror and the image formation by the concave mirror. The very interesting thing about spherical mirrors is this, that the location, size, and whether it is erect or inverted, or whether it is virtual or real, we are talking of the image, highly depend on the object location. That is not the case with plane mirrors. In plane mirror, the size is always the same as the size of the object. It is always laterally inverted. It is always virtual, but here it is very different. And then we will talk of the uses of concave mirror. Welcome to the portals of real learning. Enjoy your learning. In the case of plane mirrors, the characteristics of the image formed was what? One, the size of the image was the same as the size of the object. Second, the image was the same distance behind the mirror as the object was in front. Third, it was erect but laterally inverted. And fourth, it was virtual. Now, these characteristics do not depend on how far the object is. No matter what the object distance, these four characteristics would be the same in the case of plane mirrors. But when we talk of curved mirrors, the whole thing changes absolutely, completely. The size of the image will depend on the object distance, for instance. So in this session, we are going to learn about spherical mirrors, and there are two types, concave and convex. We'll learn about the concave mirror in this session. What is a spherical mirror? So imagine that you have a sphere and you polish the entire sphere. So the outer surface of the sphere is the reflecting surface. And you can see how the images look. This would be called a convex mirror because this is the outside, there's a sphere. Okay, I'm taking only a part of it. The outside is the reflecting part, and the inner one is silvered. So the outer surface being the reflecting surface, it would be called a convex mirror. The actual convex mirror is basically a part of the entire sphere, like this. Suppose the sphere is there and I cut out this blue part, then you can see this curvature over here. Depending on which part you make as a reflecting surface, it will either be a convex mirror or a concave mirror. If the inner surface is made reflecting, then it will be a concave mirror. So we have a surface like this. The outer one, if it is silvered, and the inner one is polished, this one, if that is the reflecting surface, then that is concave. It's a concave mirror. And if the outer one is reflecting, then that is a convex mirror. So let's start discussing the concave mirror. But before that, we need to know some terms involved with spherical mirrors. First of all, there's a picture to depict the concave and the convex. This one is reflecting in the case of concave, and in the case of convex, the outer one is reflecting. Now, if I take a small part of the mirror, very small part, it is a straight line. So any small part of this curved mirror can be treated like a plane mirror. That means the entire mirror can be seen to be a combination of many plane mirrors, many plane mirrors. Now you can imagine what happens if the parallel beam of light is falling onto this mirror and mirrors are orientated differently. So the reflected rays will go in various directions, but still they are able to form an image. We'll see how. The laws of reflection are obeyed for any ray that strikes the surface at any angle. Those laws will never be violated. So some terms. Here is a concave mirror. This one is silvered. And this is a convex mirror. This one is silvered. So some terms. First of all, this is a part of a sphere. So the center of that sphere is called the center of curvature C. The radius of curvature would be called the distance between the center and this part, P. In the case of convex, same thing. This is the center of curvature and this is the P. The radius of curvature is CP. P is called the pole. It is the geometrical center of the mirror. And the line joining CP is called the principal axis. So this is the principal axis. This is the principal axis of the mirror. Then, if I draw a straight line AB in each case, that is called the aperture, a plane surface area of the mirror through which the rays enter. That's called the aperture. Now, if I have rays coming in and hitting the mirror which are all parallel to the principal axis, then as I was telling earlier, this is one plane mirror. It will obey the laws of reflection. So this is the perpendicular at that point. Angle of incidence will be equal to the angle of reflection. Then the other ray is falling on another mirror. That will be a smaller angle of incidence actually. But all of them obey the laws. Therefore, after the reflection, all the rays come and intersect at this point F. That is in the case of concave. In the case of convex, this ray reflects like this ray reflects like this ray is perpendicular because this is the pole, this is the center, this is perpendicular, so it will retrace like that. All the rays diverge, but they seem to be coming from this point F. So this is called a diverging mirror. The rays get diverged, and this is called a converging mirror. A concave mirror is converging, a convex mirror is diverging. And wherever the reflected rays intersect, that is where the image is formed, as you know. And here the rays are actually intersecting. That is called focus or the focal point. And it is a real focus because they are actually intersecting. The reflected rays are actually intersecting. In the case of convex, though, the rays seem to be coming from F. So that is a virtual focus. And the distance FP in each case is called the focal length. The distance between the focal point and the pole of the mirror is called the focal length. If we draw a plane perpendicular to the principal axis passing through the focal point, that is called a focal plane. So suppose I have parallel beam of light but falling obliquely, then the image is still formed in the focal plane here, but not on the focus. So these two rays that are coming after reflection, where are they intersecting? They are intersecting here. So we will have these kind of parallel rays coming if the object is very far. We take it as infinity. Parallel lines meet at infinity. So if you have parallel beam coming, then we can say that beam is coming from infinity. These rays are coming from some point on the object, and the image of that point of the object is being created here. So the object was actually standing like this, but very, very far. So this point, if it is A, then this is A dashed. A dash is the image of the point A. This point is B, and a ray of light will come like this and retrace its path. So the image of B should be on this line, and therefore the image of B is this one. The image is formed within the focal plane if the parallel rays are oblique to the principal axis. But if they are parallel to the principal axis, then it is a point image formed at the focal point, either a real image or a virtual image. So that is the concept of focal length. What is a normal at the point of incidence? Well, this is a sphere. So if you draw a line from the center of the sphere, it will always be perpendicular to this surface. This is actually a tangent, and we know the property of a circle. The radius is always perpendicular to the tangent. So this dotted line here is the normal at the point of incidence. So if a ray of light starts from A and hits this point D, it will come along this red direction with angle of incidence being equal to the angle of reflection. Similarly, in the case of a convex mirror, the ray comes and strikes at D. This dotted line is the normal at the point of incidence, and the reflected ray goes along B, obeying the laws of reflection, that is, angle I is equal to angle R. The normal at the point of incidence must always be a line drawn from the center of curvature to that point. Now, let us discuss image formation. We need only two rays in order to construct the point where the image will be formed. We need only two rays. We have at our disposal many rays, but we can do this very interesting experiment. Take a shiny spoon, and this is a spoon. This is reflecting. Actually, the entire spoon is reflecting. So if you look into the mirror from this side, then that is a concave side. If you look into the mirror from that side, that is a convex side. So if you keep the concave side like this in front of you, okay, from the inner side, image seen from the inner side, then look what has happened. The face is downwards. It is an inverted thing. Whereas if you keep the outer surface in front of your face, then that is a convex mirror and it will be erect. Image in a spoon. It is a curved surface. It is not a plane surface. So we need only two rays to construct a ray diagram, as it is called, to locate the image of a particular point object. First, if we consider a ray that is parallel to the principal axis, and I'm going to draw both the types of mirrors in each case. This is concave. A ray parallel to the principal axis hits here. This dotted line is a normal because that is passing through the center of curvature, I equal to R. It will go through the focal point. In the case of convex, this is the incident ray, this is the reflected ray. The normal is this one. Angle of incidence is equal to angle of reflection, and the rays seem to come from this point F. So that is one type of a ray which is parallel to the principal axis. It will either actually pass through the focal point or seem to come from the focal point, depending on the type of mirror that you have. Second, the ray that goes through the focal point will emerge parallel to the principal axis. This is also called the principle of reversibility of light. If a ray of light were coming this way, then it would have gone this way, passing through the focal point, correct? If you reverse the direction of the ray, exactly the same trajectory will be there, reversibility of light. So a ray passing through the focal point will emerge parallel. Here, this ray is seeming to be passing through the focal point. It will emerge parallel to the principal axis. This is the incident one, this is the reflected one. This is the incident one, this is the reflected one. That's the second type of a ray. Third, if a ray passes the center of curvature, it will retrace its path, clearly because it is perpendicular. Here also it is perpendicular. Third type of a ray. Fourth, if it hits the pole, well, this mirror is exactly like this. That's a plane mirror. So it will simply obey the laws of reflection and go away as shown for each case. Now we can locate the position of the image by drawing any two of these rays. So let us start with the concave mirror. But the image formed, the characteristics of the image formed is highly sensitive to the location of the object in the case of spherical mirrors. So let's do one thing. We take a concave mirror and take an object of some size, keep it very far, let's say at infinity, and then bring it closer, 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 and see what happens to the image. Here, this object AB is at infinity, so the rays of light are all parallel to the principal axis. This one comes and passes to the focal point. Similarly, this one passes to the focal point. They intersect at this focal point. A point image is being created. This ray was coming from A, this ray was coming from B. AB had a certain size, but A and B are all intersecting at the point F. So a point image is being created. Therefore, the size of the image will be a point image highly diminished in size. Location will be the focal point, and the rays are actually intersecting, so it will be real. And one rule is, if the image is real, then it will be inverted. If the image is virtual, then it will be erect. If, let me say, image is real, then it will be inverted. If it is virtual, it will be erect. Now, all this holds if the object is real. If the object itself is virtual, then other things may happen. We are only considering real objects, that is, from where the incident rays actually diverge. That's a real object. So, the location, size, whether erect or inverted, and whether real or virtual. These are the four parameters that we are discussing about an image. So it is at the focal point, it is highly diminished, it is real and inverted. In fact, I would say if it is real, it should be inverted. All right, so that is one position. Now let's bring it closer. How close? This note is important. If image is inverted, it should be real. If the image is erect, it should be virtual for a real object. Let's bring it closer. It is not an infinity, but it is beyond the center of curvature. That is the location. Now, from A, I take two rays. One is parallel to the principal axis. It will pass through the focal point and go away like this. Second ray I'm taking going through the center, so it will retrace its path. So point of intersection of those two rays is this. Image of A is at A dash. Whereas the image of B, if I take one ray, it is going to hit perpendicularly and therefore retrace its path. The image of B should be on the principal axis. And clearly it should be here only, because the object is sitting like this, the image will all be like this. What do we observe? First of all, we observe that the size of the image is smaller than the size of the object. The size is diminished. It is not a point image, but it is still diminished. The location is between C and F, between the center of curvature and the focal point. And it is real and inverted. The rays are actually intersecting. So just stop for a moment and think. When the object was at infinity, the image was at the focal point. All right. As we bring the object closer, the image has gone away from the mirror. It was earlier at the focal point. Now it is between focal point and C. And this trend will continue for some time. That is, as the object comes closer, the image goes farther from the mirror. And the interesting thing is, the farther the image is from the mirror, the larger would be its size. So as we bring the object closer, the image goes farther from the mirror and its size increases. Third position is, we are bringing it closer. The third position is at C. Image will be at C also. We have this BA object, one ray coming from A parallel to the principal axis, passes to the focal point and goes away this way. Another ray we are taking, passing through the focal point, it will emerge parallel. So the intersection point is here, the image of A dash is here. The image of B should be on the principal axis. So since A dash is right here, B dash also will be right there only. And the size of the image is the same size as the size of the object. The location, if the object is at C, the image is also at C, and it is the same size as object, and it is real and inverted. You can see the image started from the focal point for an object at infinity. Then it came between C and F. It went farther between C and F and became bigger. As we brought the object closer, the image size increased to an extent that now it is the same size of the object. From here, if you bring the object even closer, then the image will go even farther and become larger in size. That is what will happen. The fourth position is that the object is between C and F, this one. You see where the image is now. For the point A, this ray is parallel to the principal axis, passes to the focal point and goes off like this. And another ray I'm taking that is going and hitting the mirror perpendicularly. So it will pass through the center of curvature, and this is the intersection point of the rays coming from A. So that is the image of A dash. Image of B should be on the principal axis, so that is it. Now you see what has happened to the size. It has increased. The location is beyond C, it has gone farther from the mirror, and the size this time is larger than the size of the object. It is magnified. It is real and inverted once again. Now let's bring it closer and put it at F. What do you expect? The size of the image should increase. Alright, so this object now is at the focal point. From A, I take a ray parallel to the principal axis, it passes through the focal point and goes off like this. Another ray falling perpendicularly, it will retrace its path and go from C. You can see that these rays are parallel to each other, so they only meet at infinity. The image has gone to infinity, farthest, and therefore the size is highly magnified. Farther it is from the mirror, farther the image is from the mirror, larger would be its size. The location is infinity, the size is highly magnified, and it is real. It is a parallel beam of light. They do meet, they do intersect, but at infinity. So since they do intersect, it is real and it is inverted. So till now, these were the trends. As the object came closer, the image went farther. And the image was real at all times. Since it was real, it was inverted. And the size of the image kept on increasing. So that was a trend. Now, the only one position left is between F and P, and now the whole thing changes. If the object is between F and P, then the whole thing changes completely. I take a ray from A hitting the pole, it will obey the laws of reflection, go away like this. Another ray falling perpendicularly, it will retrace its path. Now, these two rays are diverging, they don't actually meet. They seem to be coming from the point A dashed. And the image of B will be on the principal axis. So, this is now the image. For the first time, we are having an erect image and therefore a virtual image. This is behind the mirror. The rays, the reflected rays, do not actually intersect. Therefore, it is virtual. And if it is virtual, it should be erect. And it is magnified also. The location is behind the mirror. It is magnified. It is virtual for the first time and it is erect. So this is completely different. The sixth position is completely different. So putting it all together, we had six positions. 1, 2, 3, 4, 5, 6. We can make a table. What we are talking about is the position and the size of the image and also the nature of the image. We started from infinity, the position was at F, so it was highly diminished. but the rays actually intersected, so it was real and inverted. So the nature of the image is real and inverted for the first five positions. That means from infinity up till the focal point. First five positions was real and inverted. But the size kept on increasing. From highly diminished, it became diminished, then same size, then magnified, then highly magnified. So as you come closer, the size of the image is increasing. And these are the details. If the object is beyond C, then the image is between F and C. If the object is at C, then the image is at C. If the object is between C and F, the image is beyond C. And if the object is at F, then the image is at infinity. I don't expect you to mug all these things up. I definitely want you to see the trend, to remember the trend. That is, as the object comes closer, the image goes farther. And up till the focal point, from infinity to the focal point, the image is real and inverted. That is what you should definitely remember. And the sixth point you should know, when the object is between the pole and the focal point, then for the first time, the image is behind the mirror and it is virtual and erect, and it is also enlarged. That is the way the images are formed in a concave mirror. So I want to emphasize that the nature of the image highly depends on the position of the object. That was not the case with plane mirrors. Irrespective of where the object is in front of the plane mirror, the size of the image is always the size of the object. The object distance is always equal to the image distance. The image is always erect and always virtual, independent of the object distance. Not so, not so in the case of spherical mirrors. So this table is actually important, but no need to mug it up. You can construct this table yourself if you remember the trend. What happens to the image as the object is brought closer from infinity. So I have put together a small animation to help you understand the trend. I have the concave mirror, the focal point, and the center of curvature. I start with the object at infinity. Same object. So this red arrow is going to be of the same size, same object. But right now it is at infinity. Where was the image? Image was at the focal point. Okay. Now let's bring the object closer beyond C. Now the image is between C and F. The image was here, it has moved this way, right? Now let's bring the object even closer. The image has gone farther and the size has increased. Farther the image is from the mirror, the larger is going to be its size. Now let's bring the object even closer to the point C. The image, as you can see, has gone farther and the size has increased. Bring the object closer between C and F. The image goes beyond C and for the first time it is magnified. But all the time it was inverted and real. Bring it to F, the object at F. The image is highly magnified and goes to infinity. These were the first 5 points. The sixth point is different. If you bring it between the focal point and the pole, the image is being formed behind the mirror. It is virtual, erect, and magnified. I hope this animation has helped you to understand the trend. So let's talk the uses of concave mirror. One is car headlight. This is not exactly a spherical mirror. The shape is more like parabolic. But if I consider a small part, if this is nearly a sphere, the bulb of the headlight is placed at the focus or the focal point of this spherical mirror. So the rays strike the mirror and they come out parallel to the principal axis, every ray. But since we want a big parallel beam, then it should not be completely spherical. It leads to a situation of a spherical aberration. If you make it parabolic, then all the rays that come out are parallel. It is not a spherical mirror, but it is a curved mirror. It is a curved and concave mirror. So the use of this concave mirror is to produce perfectly parallel beam of light and a very broad beam of light, not a narrow pencil of light, very broad beam of light. The concave mirror can magnify if the object is between F and P. And that magnification is very unique. It is the only time that the concave mirror produces an erect image. If the object is between F and P, then the image is erect and virtual and magnified. So we use that characteristic for makeup mirror or shaving mirror. You want to see your face more clearly, so it will appear bigger. But the focal length of the mirror should be large enough because your face is the object, right? That object should be between the focal point and the mirror. Your face should be between the focal point and the pole of the mirror. That means the focal length of the mirror should be large enough so that your face can fit inside that space, in that region. Dentists use this mirror only to see a magnified image of your tooth. It's a tiny concave mirror. We make a very giant concave mirror and we can create a solar furnace. Sunlight is nearly parallel beam of light coming. When it hits, all the rays will come and converge at a point called the focal point. At that focal point, whatever we keep, all the energy of the sun is getting focused at one point. Therefore, the temperature would rise and it can start burning. It is a solar furnace. But obviously, the position of the sun keeps changing from time to time. Therefore, the mirror orientation should also change. So that all the time, the incident beam of the sunlight after reflection focuses on that particular point. So there are such solar furnaces in the world. Right. So that was concave mirror. In the next session, we'll talk of convex mirror and we will do some numericals on this topic of spherical mirrors.